So as an extension of 3.9, we're going to talk about logarithmic differentiation. So we have three very challenging problems here that we're going to try to solve with this technique. So the idea is anytime you have a function raised to a function, so f of x raised to the g of x power, we're going to need to use what we call logarithmic differentiation. So we're going to start by taking the natural log of both sides of the equal sign. That will allow us to use our property of logarithms on that right side and change that function raised to a function into a function times the natural log of a function. Now we can use implicit differentiation on both sides. So we're going to get du over u, or 1 over u du. Then on the right side we have a product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. And we can clean up a little bit, and we're going to multiply that y to the other side. So we might want to write that as cosine over x, or 1 over x times cosine x. That's going to be a minus, and I don't know if there's a great way to write that. I'm going to call it sine x times natural log x and try to make sure that we know that neither one of those is in the other function. And then finally, we're going to replace that y by what we knew y was equal to. So it's x to the cosine x power times cosine x over x, and then minus this kind of weird sine x times natural log x. Okay, same idea on the next one. We're going to take the natural log of both sides, then we're going to use our properties of logarithms to bring that function that's in the exponent out in front and make it into just an ordinary multiplication. We'll do implicit differentiation on the left, and we're going to use our product rule on the right. We'll multiply that y to the other side. Notice x times 1 over x is just 1. And then we can go back to writing the y as the function x to the x. Sometimes it's also used just when you have this miserable looking expression in the green there. We don't have to use logarithmic differentiation here, but it would be an awful quotient rule, product rule, chain rule mess. So sometimes on these, it's just nicer to take the log of both sides and then go from there. So I'm going to start writing that in a more logarithm-friendly form. So I'll write that as x minus 2 to the 1/3, and we already have that x plus 4 to the 3/4. So then we can, on the right side, use our properties of logarithms. So that's going to be the log of x squared times x minus 2 to the 1/3, and then we'll get a minus natural log of x plus 4 to the 3/4. And let's keep doing some more properties so we can make this into the sum of the logs, and then I'm going to go ahead and do two steps at once and write that exponent out in front. That's going to be a plus 1/3 times the natural log of x minus 2, and then the minus 3/4 times the natural log of x plus 4. Okay, now that we have done all our prep work, we can do our implicit differentiation on the left, and the derivative of natural log x is 1 over x, and we'll get 1 over 3 times x minus 2 from that next one, and a minus 3 on top, 4 times that x plus 4 in the denominator. We can multiply that y to the other side, and then go back to calling it that awful x squared cube root of x minus 2 over the x plus 4 to the 3/4, and then have that 2 over x plus 1 over 3 times x minus 2 minus 3 over 4 times x plus 4. That's just messy any way you look at it. Let's go to the next panel and let's see if we can figure out what to do with this. So we have the spread of a rumor at LHS is given by R of t is 1,000 over 1 plus e to the 5 minus t, where R of t is the number of students who have heard the rumor t hours after it was initiated. So we're going to need our calculator for this. Estimate the initial number of students aware of the rumor. So we're looking for here R of 0. So that's going to be a 1,000 over 1 plus, and that's going to be e to the 5th. This I think we want to throw into our calculator, and I believe that's going to be about, let me make that approximately 7 people were in on this right from the get-go. Now, how fast is the rumor spreading after 5 days? We need to find r prime of t and then evaluate that at 5. Okay, this is going to be a bit of a challenge. I'm going to do our, I think, quotient rule here. So there's 1 plus e to the 5 minus t times the derivative of 1,000 minus the numerator times the derivative of the denominator. And the derivative of the denominator is going to be that same e to the 5 minus t, then times the derivative of the 5 minus t, which is going to make that as a -1, which will make that be a plus. And then we're going to get this 1 plus e to the 5 minus t whole thing squared. So it looks like that's going to be 1,000 times e to the 5 minus t all over 1 plus e to the 5 minus t quantity squared. Then we're going to evaluate that at 5. So from there we want r prime of 5. So that is going to be, I think we can do this without a calculator actually. So we're going to get 1,000 on top because 5 minus 5 is 0, e to the 0 is 1. Likewise in the bottom, we're going to get e to the 5 minus 5 is e to the 0, which is 1, plus 1 is 2, squared is 4. And so we're going to get 250, and our units there are going to be people per, well, I said days, scratch that. This is really hours in our world. So that's going to be people per hour. So I guess you could say that rumor is really on fire. 250 people per hour are hearing of this rumor. It's not going to take it long. In fact, by that time, maybe the whole school knows what's going on. Okay, now it gets really tough. When is the rumor spreading the fastest? So what we want to know is, here is the spread of the rumor. So it's really a rate of change of the rate of change question. So what we need is to know what is r double prime of t, and then we're going to try to see when is that at its greatest. So where is that second derivative equal to 0? Oh boy. Here we go. So we're going to take r double prime. So we're going to take the denominator. That's the 1 plus e to the 5 minus t squared times the derivative of the numerator, which is going to be 1,000 times that e to the u du. So e to the 5 minus t, and then the du is going to be a -1. Minus the numerator, there's our 1,000 e to the 5 minus t times the derivative of the denominator. Okay, hold on here. 2 times 1 plus e to the 5 minus t to the first power times the derivative of the inside function. The derivative of 1 is 0. The derivative of e to the 5 minus t. Oh, hold on. There's my left hand coming in to haunt me here. So that's going to be e to the u, e to the 5 minus t times a -1. And then that's going to all be over the denominator squared, which is going to be 1 plus e to the 5 minus t, whole thing now to the fourth. Okay, let's put on our algebra hats here and see what we can factor out. It looks like we have a factor of 1 plus e to the 5 minus t in both of those. That sounds right? So I think a 1 plus e to the 5 minus t. Looks like we also have what? It looks like we've got a 1,000 e to the 5 minus t and even a negative of those in each of those terms. So I think we can factor out a negative, and then I'm going to say 1,000 e to the 5 minus t that we're pulling out of both of those. I think that might be about it. Let's see what that leaves us. So we took out one of those. So this first term has a 1 plus e to the 5 minus t in it. We took out everything on there. So we took that out. We took out that. So we took out, I think, did we take out the negative on that also? I think we did. So that's going to be just this 2. I think it's now up to a plus. So plus from there, 2. We took out that 1 plus e to the 5 minus t. So I think we just have that negative. So I'm going to maybe make that negative 2e to the 5 minus t. And that's all over 1 plus e to the 5 minus t to the fourth. Okay. Well, we can cancel one of these. That's not really going to make a whole lot of difference. Now, this is our second derivative, so I think this is good enough for us for our second. Well, we can maybe do a little bit more. We can simplify inside that brackets. So we have a negative 1,000 e to the 5 minus t times, and that's going to be a 1 minus e to the 5 minus t power all over, and then we have 1 plus e to the 5 minus t quantity cubed. So there's our second derivative. We want to know where is it equal to 0, and the good news is that we don't have a lot of choices here. Now an exponential is never 0, so this is not going to make anything 0. This is never going to be 0. So essentially what we get to do is say just that 1 minus e to the 5 minus t equals 0. That's the only place that second derivative could be 0. And so that means that 1 is equal to e to the 5 minus t. And so that means that an exponential e to a power is 1 only when that numerator, 5 minus t, is 0. And that means that t is going to be 5. Now that's where it's equal to 0. Now the only thing we have to argue is that's where this is increasing at its fastest. So that is, we want to know on either side of 5, is this, I'm trying to think what color to make it, is this expression going from positive to negative or negative to positive? So the claim is that this denominator is always going to be positive, that no matter what we plug in, this exponential is always going to be positive, times negative means this is always negative. Now, to the left of 5, when t is something smaller than 5, then we're going to get something like, say, e to the 5 minus 4. E is bigger than 1, so this is going to be a negative. So we will get a negative times a negative. So if we're doing our number line here, and there's 5, we're going to get a negative times a negative is positive on the left side. And when t gets bigger than 5, say 6, we're going to get 1 minus e to the negative 1 is 1 over e, which is roughly 1/3. that's going to go back to positive, and so it will in fact change sign at 5, which means that that t equals 5 is indeed when the rumor will be circulating its fastest. It will be growing the fastest, increasing the fastest. Crazy, crazy, crazy. These kind of functions we'll actually see much later. They are known as logistic growth functions. So we'll talk much more about those down the road here a little bit. Very good.